Today, we're going to teach Moondream to watch an NBA game and to detect the player with the ball. We're going to get started up for Lens, the official Moondream fine-tuning platform, then doing the fine-tune itself, and finally deploying the fine-tune to production. I'm Ethan, founding scientist and head of post-training here at Moondream. Let's hop into it. Let's get started by going to moondream.ai, heading over to the Lens page, and hitting the docs. Here you can see that we offer two forms of fine-tuning: RL, reinforcement learning, and SFT, supervised fine-tuning. For our fine-tune today, player with the ball, RL is a good fit. This is as the model is already showing some signs of life on the task. We can see that the model produces some false positives, but it does get the player with the ball. So there's behavior that we can then reinforce. We would want to use SFT if we were doing a task that would be impossible to know with general information. For example, if we had an internal part number for a product, there would be no way for the model to know this based on general internet information. So the best starting point would be SFT. But in this case, this is a pretty general, simple fine-tune. So RL is how we're going to start. So very first thing, let's actually sign up for Moondream. Let's go to that Lens page and click on the top right-hand side and hit console. This will bring you to the Moondream dashboard. Here, you can go ahead and sign up for an API key. This is the key that you'll use to make inference and fine-tune requests. People who are new will need to create a key for the first time. So go create API key, and then you can copy it. If you don't copy it, no worries. It saves so you can see it again later. When you sign up for Moondream, you get $5 a month free. And this happens every month. So it's a good amount to get started with doing a small fine-tune or trying to make some requests to the cloud. On the left-hand side, you'll see fine-tunes. When you create a fine-tune, it'll populate here. And if you click on one, you can see information like metrics, training steps, and the checkpoints that you save. Let's first look at the data. So we have the data up on Hugging Face. We kept it pretty simple. We have the image, the prompt, and the bounding box for the player with the ball. We're going to access this just through load dataset with transformers. So let's hop over to the code. Here we're using the Moondream Python SDK, which can handle inference and fine-tuning requests. When we create a fine-tune, there's a couple hyperparameters that we have to set. The first is batch size, which is the number of unique samples that are going to be included in every training step. Because we're using reinforcement learning, the model is going to make a couple predictions per sample. So here we're requesting 4 predictions for every sample. And let's have a look at what that actually means. So here we gave the model this image with the prompt, player with the ball. It made 4 different predictions. Some are good, some are bad. And it's our job then to score these and to give the better results a higher score to reinforce this behavior to the future. So as we see here, we have this prediction. It's close, but not perfect. It does get another player to the right of the guy with the ball, but it is somewhat close. So here the reward that we're using is MIOU, mean intersection over union. It's a good fit here because our bounding boxes are pretty accurate, and we only have samples where there is a player with the ball. So in the case where the model makes multiple predictions, these extra bounding boxes will add 0 to the sum, meaning that the mean will decrease. So this sample and this sample right here, pretty similar bounding of the player with the ball. But in the second sample, we see that it produces extra false positives. But this brought the reward down, which is the behavior that we're looking for. So throughout training, this sample will become more likely to happen again in the future. Once we set these, we can then go ahead and set learning rate. Because this is a pretty simple fine-tune, we chose a rank of 16, which is how big the LoRa that we're training is. If we were doing something more complex or we needed additional representational capacity, we could bump this up to 32, but 16 is totally fine for object detection. And with 16, a learning rate of 2e-4 is a safe starting point, and is what I would recommend. So once we set these hyperparameters, we can get started by actually loading the data set. We can just use load data sets from Hugging Face, and then we're going to want to loop through that. So we do that here. This is the data that we're then actually going to loop. And then we get into the chunk of the code where we do the actual fine tuning. So to create a fine tune, very first thing you want to do is register it. So you can go md.finetune or md.ft. This will take your API key, you're going to give it the name of the fine-tune, and then you're pass up that rank. This will then return a fine-tune ID. Because Lens is distributed and asynchronous, you can stop the train at any point and resume it later. You can change the data that you're passing up. All this is pretty flexible. So to resume the fine-tune, all you have to do is pass up a fine-tune ID. If you don't remember your fine-tune ID, it's also totally fine. On the Moondream dashboard, we have the fine-tune ID right here. So you can copy that and use that to resume. So now that we have our fine-tune itself, we're going to want to start looping through our data. So we have our data, we'll pass it to ft.rollout_stream, and this is what's going to create those Moondream predictions. Once we get those, we can then score them, which is what we see here, scoring each prediction. And then we're going to want to pack that into a batch. Once we have a batch, in this case of size 24, we're going to do the train step. This is when the model actually updates itself. So here to do that train step, we go ft.train_step, pass the batch, and then pass the learning rate. If we were doing something more complex, like something with reasoning or math, a much larger fine-tune, we could anneal that learning rate over time. But there's no need to do that here. So we're going to just make learning rate a constant like we did up top and pass that in using the same learning rate for every step. While the model trains, you're going to want to make sure that it's healthy. So first thing to look at would be reward mean. This is a straightforward fine-tune, so we're not changing what the reward function is. We have one constant reward function, MIOU. Because of that, we can think of reward mean as a proxy for how the model is behaving and improving. We would hope to see this going up and to the right, which we do here. It means that on the training data, on average, the model is producing a higher MIOU. But this isn't everything. We want to know how the model will perform in the real world, which is where the eval comes in. So looking at our data set, we have 108 train rows and 20 test rows. We don't train on the test data. So this will give us an idea of how the model would perform if we handed it off to real users. Just like the reward mean, we would hope to see this moving up and to the right, which is exactly what we see. At the beginning, we get 40%, and by step 30, we're already at 54%. So these are signs that the model is learning and is healthy. If something was going awry, you might want to look at grad norm or KL, but this is a pretty straightforward fine-tune. So if reward mean is going up, MIOU is going up, it's safe to assume that this is a healthy fine-tune. So while the numbers are great, it's always important to look at what is actually happening in your model. Look at the data. So by hopping over to train steps, you can see what you passed up every time you did ft.train_step. Here, like I said, we passed up this image with these bounding boxes that Moondream predicted. And this is really important to look at because you want to make sure that your reward makes sense. Is this a behavior that you want to reinforce? So making sure that what you're actually scoring lines up with your intentions for the fine-tune. So the qualitative measurement looks great and the quantitative measurement looks great. So we're going to call this a healthy, stable fine-tune. As this model learns, we see that it drastically improves. So looking at the F1 metric, base Moondream gets about 28%, but the fine-tuned Moondream gets about 79%, beating the large frontier models at about 53%. This fine-tune ran for 60 steps, took a total of about 54 minutes, and cost close to $17. So for about $17, we were able to take Moondream from under what large frontier models could do to significantly outperforming them. And if we hop back down to the before and after, we can see at the beginning, we have all these false positives, but after the fine tune, Moondream was pretty confident about just picking the player who actually has the ball. Let's go ahead and deploy this fine tune in production. The first thing we want to do is actually save the checkpoint, which we can do with ft.save_checkpoint. This will make that checkpoint available for cloud and local use. When you save a checkpoint, it'll also pop up in your dashboard under checkpoints. These are the training steps that you can hit when you want to try it in cloud or run it locally. To run it locally, we use our Photon fast inference backend, which is baked into the Python SDK. So let's actually do that here. I've already saved a checkpoint, so Let's just try hitting it. We can hit it just like we would hit the standard Moondream. All we have to do is pass fine-tune ID and give it the step. And if you don't remember that fine-tune ID, once again, that's okay. We have it here in the dashboard. So let's actually make that request. Go Python, detect player with the ball. Okay, so that took our image, passed it up to the cloud, hit our fine tune, and returned back the bounding box for the player with the ball. All we had to do was when we made that request, we passed in the fine tune ID and the step that we wanted to hit. And remember, this is the step of the checkpoint that we had saved. If we wanted to run this locally, all we'd have to do, pop over here, go local equal true, and then this will run on my machine. You can do this if you're running Apple Silicon, Windows, or Linux. If you're on Linux, we support CUDA GPUs of the Ampere, Hopper, and Blackwell architecture. Today, we fine-tuned Moondream to watch an NBA game and find the player with the ball. If you have any questions, reach out to us on Discord or shoot us an email at contact@moondream.ai.